And the next thing we want to look at is what the actual detectability of gravitational waves might be. So let's just imagine the following setup. We're going to have gravitational waves propagating along the z-axis. So going along the z-axis such that they're stretching and contracting along the x-axis. And we can imagine 2 points along that axis. And they have positions. XA is just at the origin for simplicity. And XB is at some distance. 0, 0. And of course they also have initial velocities. And they're stationary, so U alpha A equals U alpha B. And then in 4 dimensions, that's 1, 0, 0, 0. And we can then calculate the change in the coordinate positions as a wave comes through. And that's just via the geodesic equation. And here I'm just interested in the spatial components. And so what this comes down to basically is calculating one of these connection coefficients for the ith position and the time components. And we know, because the perturbation is small, that the Christoffel symbol is also small. What that means is, to first order, we can write something like this. I'm not quite sure I've got this the right way around. Let me just double check in my notes, because my notes that I've written here are a bit incorrect. HTJT. Apparently right, TJT. Of course, because of symmetry here. HTTJ. In practice, it doesn't matter what you write there, because the answer is that it is equal to 0. And what that tells you, rather surprisingly, and this is something that I think confused people in gravitational waves for some time, it tells us that the coordinate positions of 2 points don't change as with the passage of a gravitational wave. So as the gravitational wave comes in, the actual coordinates that you're in don't matter. And that's not so surprising, because if you think about, say, the Earth, which might be stretched and squashed by gravitational waves as it comes through, your longitude and your latitude don't actually change, right? Your coordinates don't change, but the actual physical distance does. So that's the important point. The coordinates don't change, the physical distance does. And what that means is you couldn't actually measure that change in distance, by example, laying out a set of rulers and then looking at how the sight distance changed with time, because the rulers would be stretched along with everything else. So you cannot measure this distance with the ruler. What you need to do is to look at the physical distance, and that's why, as we'll get on to, you actually use a time of flight measurement. Remember, the speed of light is a constant, so if the physical distance changes, even if the coordinates don't, the light travel time will change. So the physical distance does, and the physical distance is just found from a line element along the x-axis. That's the modulus of the determinant of the metric. Oops, sorry. Skipping a step here. One minus a half a. And the reason this looks like this is because if I go back up here to where I've got my gravitational waves, this is what the gravitational waves look like, and here the A's are being used to define basically the amplitude for a wave propagating in Z, oscillating, or the change in the X direction. And so what you have here is you have this change in length, which is this, i.e., if we write delta L as a function of t over that initial separation, it's just equal to minus a half a. And more commonly, we'll write this as delta L over L, and that's a quantity known as the gravitational wave strain. You'll also see that essentially as H, that is your perturbation, if you like. And so you can see that if you want to detect a small L, delta L, then a large L helps. But before you can decide on that detection, you need to actually work out whether there's anything that you can detect in the first place. So then you need to look not at how you detect them and how they propagate, but how you generate them.